And here's part 2 of our journey into a mathematical model of motion. So now we're going to graph velocity in one dimension. You'll be able to determine from a graph of velocity versus time the velocity of an object at a specific time. Interpret a VT graph to find the time at which an object has a specific velocity. And you'll calculate the displacement of an object from the area under a VT graph. So velocity versus time. You can see on this one that the x-axis is time. Again, just like with position versus time, except now we're doing velocity. So our x-axis is time. Our y-axis is the velocity. Remember to put your units on there. Meters per second. Seconds. Slope of the line equals the acceleration. Why is that? Because rise over run. Change in y over change in x. In this case, it's change in velocity over change in time, which lo and behold is acceleration. Because you get meters per second over seconds. And acceleration is measured in meters per second squared. So that's how that works. You can have different velocity versus time graphs, just like different position versus time graphs. So here you can see that your velocity, it's pretty steeply negative here, so that means a fast velocity. It means a fast acceleration, I'm sorry. And acceleration starts to slow down as your velocity goes to 0. And here, same thing, except for now you're slowing down faster. Because remember, the slope of this line is the acceleration, so the steeper the slope, the greater the acceleration. You're slowing down a little bit, put your brakes a little harder, a little harder, a little harder, slam on them because you don't want to hit that child crossing the road. So you stop really quick. Or you could have a nice straight line. This nice straight line means you have a constant acceleration. And I can't spell constant. Constant. Constant acceleration for this guy and this guy. Straight lines, constant acceleration. And over here we got changing accelerations. Changing acceleration. See, acceleration here increases as time goes on, and here it decreases as time goes on. So horizontal lines mean a constant velocity. A sloped line equals a changing velocity. Then the steeper the slope line, the greater in change velocity. And negative means deceleration, which I hate that word. I don't know why I even wrote that on there. It means negative acceleration. You can also have acceleration versus time graphs. We usually don't draw these in physics. The only time we use them is for finding the change in velocity. So time on the x-axis, acceleration on the y. It shows how acceleration changes over a period of time. So here you can see acceleration is constant. What's a constant at? Looks like 9.81. So what's this acceleration in here? Talking about gravity. Now if you find the area under this graph, sorry for my not straight lines, you can find out how far something falls in a given amount of time. And why is this? Because what shape is this? This is a rectangle. It has a height of 9.8 meters per second squared, and it has a length of, I guess it started from the 1, so 1 to 10, so it has a length of 9 seconds. And how do you find the area of a rectangle? It's length times height, so 9 times 9.8. If you put your units in here, 9 seconds times 9 meters per second squared, you get roughly 90 meters per second. So that's how much your velocity changed in this 9-second time period. Which makes sense because we know for free fall your velocity increases by 10 meters per second for every second. So if you increase your velocity for 9 seconds, you're going to have 90 meters per second. And that's how I already said acceleration. We usually use constant acceleration in CP physics. We're usually going to alter acceleration too much. So all three graphs put together. Here's your position versus time graph up top, your velocity, acceleration. Now all these represent the same exact situation. So here we can see our velocity is slowly increasing. It's getting bigger, 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 and bigger, bigger. Just here, velocity is low, but it gets faster and faster and faster. And since this is a straight line, we have a nice horizontal line for our acceleration. Now inflection points, velocity starts to change. Velocity starts to get negative. The slopes of tangent lines start to decrease, which we can see starts to decrease. This point right here, velocity is 0. We drew a tangent line right here on our graph. The slope of that line would be 0. So your velocity better be 0. But the whole time, since this is a nice, even, straight line, and it's pointing down, it means we have negative acceleration. So we have a nice horizontal line for negative acceleration. All right, back up here. Next critical point, position is 0, but we're changing concavity, so an inflection point, which means we're going from a negative velocity back to an increasing velocity. And I'm sorry, that means acceleration. Acceleration is changing. You can see it goes from a negative acceleration to a positive acceleration. So in real life, note how the V graph is pointy and the A graph skips. But in real life, the blue points would be smooth curves and the orange segments would be connected. So in real life, you wouldn't have these such sharp points because you can't just like stop on a dime. There's always a little lag time. So these would be curved in there. And then these guys, you might have a pretty steep line, but it'd still be connected. Unless you're, the magical roadrunner, then you can just start and stop on a dime. So constant rightward velocity. This is how your position, velocity, and acceleration versus time graphs would look. So we have a constant velocity, so we have a nice horizontal line for our velocity. It's constant velocity, it's not speeding up or slowing down, so our acceleration is 0 the whole time, and our position steadily increases over time. A constant leftward velocity, your position goes from 0, you're going backwards, that's why it's getting negative. Since it's constant velocity, you're still going to have a nice horizontal line at a certain velocity. And also because it's constant velocity, it means there's no acceleration, so acceleration is still 0. Constant rightward acceleration. Maybe that should be leftward. Yeah, it should be leftward. No, because you're speeding up. You're starting back here. That's why I did this. Okay, you're starting right here at 0, but you're moving backwards. Your velocity is increasing. Goes from negative 20, you turn around right here. Goes negative 20 to 0. Acceleration, since it's the constant acceleration, you have a nice horizontal line. Constant leftward acceleration. You can see that this ball is slowing down. Your acceleration is leftward, your velocity is rightward. It means you're slowing down. You can see in your position versus time graph how we slow down until we reach 150. You can see that from your velocity versus time graph because it's a negative slope. It means you're slowing down. The acceleration is a constant negative value, so it's just a horizontal line. Leftward velocity with rightward acceleration. See if you can figure out what's going on here. Actually, same exact thing that I had before, a couple slides ago. Leftward velocity means your position is decreasing because you're going to the left. Your velocity is increasing because you're accelerating positively. That's why your acceleration line is positive. And area under a VT graph. If you calculate the area underneath a velocity versus time graph, you'll multiply the height times the width. Because height is actually velocity and width is actually time. So velocity is meters per second, times in seconds. You multiply meters per second times second, you get meters. And therefore, it's equal to velocity, time. Forget that for right now. This one shows it. So remember, the velocity equals distance over time, or change in x over time. You should have got from your chapter outlines. Rearranging this, bringing the delta t over to this side, we get to change in your x position, your distance, equals velocity times time, which is just rearranging this equation. So that's how you can get this equation from a graph, because you're just finding the area under the velocity versus time graph. And therefore, the area under a velocity versus time graph is equal to the displacement during that time period. So note here that the areas are about equal. Like this area here is pretty much equal to this area here. So even though significant distance may have been covered, like you travel this whole distance, because this is your position versus time graph, you travel this long distance, the displacement is about 0. So you started here, you stopped right down here. So it's not quite 0, but it's pretty much 0. If these two, positive area, negative area, if they're about equal, you end up in the same place you started. Because when you add those areas together, it'd be 0. Velocity versus time, the area, just a little recap, and then we're done. The area under a velocity time graph indicates the displacement during that time period. That's an important fact to remember. And the slope of velocity versus time indicates the acceleration. And the smaller the time units, the more instantaneous is the acceleration at that particular time. So if you measure between two really small time intervals, you're going to get more instantaneous. Don't really worry about that. I mean, if we were doing calculus-based physics, that'd be really important. Just good to know, though, for now. And if velocity is not uniform or is changing, the acceleration will be changing and cannot be determined for an instant. So you can only find an average acceleration. So if you have like a curvy line, it's kind of hard to figure out. So you just want to find your average acceleration. Instantaneous is a little tricky. That's it.